Hello, I'm Diego Calderón. I'm a postdoc at Charles University in the Czech Republic, and would like to tell you about my research about the stellar winds pumping the heart of the Milky Way. Um, this research investigates the very center of our galaxy, the central region where there's a supermassive black hole. Its vicinity is populated by hundreds of O-B-type stars, very massive and young stars. Out of them, 30 are Wolf-Rayet, which that possess powerful outflows in form of stellar winds, very high density, and accelerating up to high speeds. This region is filled with a lot of material that shines in the X-ray due to the presence of the stellar winds, and in total they supply a rate of 10 to the minus 3 solar masses per year. However, the accretion onto the supermassive black hole is way lower. So what happened to the rest of the material? Does the material piles up in the very center or is it ejected away? However, there's evidence that in the past, the black hole might have been more active because there are X-ray echoes that are observed from molecular clouds at hundreds of parsecs from Sagittarius A star. That suggests, therefore, a higher activity in the past. Also, the X-ray spectrum of Sagittarius A star seems to be better reproduced with an accretion flow that considers an outflow solution. And on top of this, last year, Murchikova reported the presence of a disk-like structure around Sagittarius A star, observing the H30 alpha line with ALMA. So you see this double peak emission. So we don't understand how the material can cool down and settle on a disk-like structure. To investigate these issues, we develop a numerical simulation using Ramses. We consider a cubic domain in 3D, of a cube of size 1.6 parsecs. We consider the supermassive black hole, the stars that orbit around on Keplerian orbits, and they eject winds. So we follow and model the evolution of the gas that is ejected into the environment and how it moves around in the presence of the supermassive black hole. Fortunately, the orbits of the stars is well constrained because thanks to the decade-long monitoring of the region, we know their positions, their proper motion, the line of sight, velocity, the mass loss rate of the winds, and the terminal velocity of the winds. So we integrated the orbits firstly backwards in time, and then we start the evolution of the hydro simulation from the past until the present. So specifically, we integrated the position of the stars to the past to 3,500 years ago. And from then, we start the simulation up to the present to recover the present state of the system. And this is what you see now. Here you see the simulation, an animation of the simulation, going from the past up to the present at t equals 0. And here you see the motion of the stars around the supermassive black hole while they eject their winds. This is a density map of integrated density along the line of sight. And here you see how the winds fill the domain relatively fast, and some winds interact, some cool down, and some material seems to settle around the center of the simulation domain where the supermassive black hole is. If we make a zoom in the last snapshot, we observe clearly it looks like a disk-like structure, which resembles the disk-like structure reported by Murchikova. So from our study, we observe that cold material accumulates as a disk-like structure around Sagittarius A star, only if we model for long timescales, because previous work didn't model it for long enough. So given the duration of the Wolf-Rayet phase, this likely already happened. And if so, The warp-based stars could be responsible of all the phenomenology observed. The disk-like structure, the more active paths, and the current outflow taking place. So here I leave you with my conclusions, and thank you very much. Please contact me if you have any further questions. Thank you.